All right, gang, Math 5500. I'll just tell you, be very transparent. I have had a heck of a time getting this video posted. Uh, Seems like every time I try to post it, something happens. So we'll see. It's all right. It's part of the job. Uh, all right. Purpose of this video is to look at it, confidence bands for predictions, and we'll use what's called the working hoteling 1 minus alpha approach. And what this does, it gives us two bounds for any particular x sub h value. And just kind of a little bit of review. Confidence intervals in general take an estimate plus or minus the margin of error, where the margin of error is the critical value of the probability distribution times the standard error. Well, in this case, what we have is we have the predicted value of y at the x sub h, plus or minus this w, which I'll explain in just a second, times the standard error for the sampling distribution of the predicted values. Now, just so there's no misunderstanding, this y sub h is, y hat sub h, I should say, is very easy to find. Just insert x sub h into our model. The standard error is simple. We've done that before. Recall that the variance, and of course we'll have to take the square root of this, is equal to the mean square error times 1 over n plus some stuff. And that stuff is actually the difference from the value to the mean squared times the sum of the deviations of x. And obviously the summation runs from 1 to n, where n is our number of data points. Now the only thing new really is w, and it's actually expressed as w squared to begin with. And this is easily found by just taking 2 times the f distribution, the okay, 1 minus alpha level with degrees of freedom 2n minus 2, I believe. Let me think about that one. Yes, yeah, 2 degrees, yeah, okay. And that's, with R, this is really easy to find. We just use QF, and if we want the 95% confidence interval, then alpha is 0.05, so we'd use 0.95, 2 degrees of freedom, n minus 2 degrees of freedom, and just multiply by 2, and then take the square root. I think that's all I want to cover here. I can't think of anything else. Let's move over into R. I've already I want to keep this video small because I want it makes it easier to upload. So what I did is I just went ahead and worked all of this in R. So let me get to R. Let me just minimize this and. All right, so what I did is first line, just set my working directory, got my data attached, and got the head. Head, again, gives you the first 6 lines, 5 or 6. One thing that is pretty strange, well, there's many things strange about me, but one thing's really strange about me is when I teach, I use R. But when I work on a project myself, I use RStudio. So if you want to investigate RStudio, it saves a lot of time, and it's really nice if you're going to save scripts and work, save a script and then use it on another data set. So, and there's other advantages too. I'm not really sure. I'm sitting here thinking, why do I teach with R, but I use RStudio? I do not know. It's just, just too old and too stubborn to change. All right, so you can tell from the model what I wanted to do is I want to predict body fat from triceps. So the first thing I need is the mean square error. And I'm going to find that the easy way, and that's using R. So I use ANOVA, and of course the mean square error will be the mean square for the residuals. So I went ahead and saved the mean square error as 7.95, much faster, and I may even argue more effective in a sense than working it out by hand. Because, it's easy to make typos. I do it all the time. Next thing I wanted to do is just get an indication about what the triceps look like. This is not something I typically do. This is for a teaching and illustration purpose. So the mean is 25.3 and the range is 14.6 to 31.4. So the smallest tricep measure we have is 14.6. The highest is 31.4. Now what I want to do is I want to illustrate that when we choose an x sub h close to the mean, that the variation is much less in the confidence band than far away from the mean. And you'll really get, at the end of this video, you'll get a visual where I do, I'll create a scatter plot with the confidence band included on the graph. All right, so the next thing I do is I just I do the predicted value for 25, and I do the predicted value for 31. This is equivalent to finding the model and just taking the slope plus or minus 25 times, taking the slope times 25 and adding or subtracting the intercept, and then doing the same thing for 31. Next thing I did is I found the deviation for 25. This is just taking the x sub h minus the mean squared. That's the numerator part of the last part of the variance. So I did that for 25 and 31. The next thing I did is I found the denominator, and I called this the sum of the deviation squared. So this is actually the denominator in the far right part of the variance for the predicted y's. Next thing I did is I created the w. You can see I took the square root, because this part right here will create what we call the w squared. So I'm calculating a 95% confidence interval. Guys, again, remember the F distribution is a right tail distribution, right? That's where all of our rejection region goes. So we don't have a two-tail, so we don't, we just look at the area to the left of that critical value. Of course, the 2 is, and then what I do here, I took the length, which is just the sample size minus 2. I always think it's strange for R to find sample size as length, but maybe there's a reason. So the next thing I do is I calculate the 95% confidence interval, but the first thing I need to do is calculate the standard deviation. So I calculated the standard deviation for 25, and I calculated the standard deviation for 31. So then I calculated the confidence interval, the left bound, the right bound, so I get 18.9, call it to 21. And for 31, I get 22.6 to 27.6. So you can compare the widths for the x sub h equal 25, which is very close to the mean. We only have about a 2.1 difference, right, from the upper bound to the lower bound of the confidence interval. But when we move over to 31, which is quite a distance from the mean, relatively speaking, we have a difference of about 5 units. Now the next thing I want to do is I want to create the scatter plot with a confidence band. So what I have to do here is I have to create new data that focuses solely on, now let me explain this. The reason I put data here is because that's the name of the old data set. Hold on, I got one of my GAs calling, and I want to let her know I need to call her back. Seems like every time I've started a video today, something has interrupted, but that's okay. Not complaining. All right, where were we? Okay, to start out, I have to create a new data, and what I do here, this is just a function in R, where I can take the data set. So if I had named my initial data set way back here, if I had named this Peter, Paul, and Mary, I'm dating myself, I don't even know where Peter, Paul, and Mary came from, then I would have to put Peter, Paul, and Mary right there. So yeah, I'm looking at the variable triceps and body fat for a reason, and I got to attach it. When there's data included in, I'm sorry, when there are variables included in Peter, Paul, and Mary, where the hell? Anyway, when there is variables in a newly created data frame, right, that was used in another, it will call that it is those variables have been masked. All right. So anyway, I don't even know if I need this part because I created this above, but because I created a new data frame, I wanted to just be safe and create that. Next thing I do is I do my predictions for the model. Now, what this allows me to do is specify the type of prediction I want to make. Now, this is something you need to tattoo to the brain. It's something that you need to write in your notes with big old flashing neon lights around it. If I want to find the mean response, which makes sense because I used the variance, I used the mean square times the quantity 1 over n plus, the right side. If I had used the prediction for a new value, and this is demonstrated in the previous video, then I would have that extra 1 to the right of the mean square error when calculating the variance. Well, if I need that prediction, I need to type prediction there instead of confidence. But I want to be consistent with the calculations I made above, where, again, I had the mean square error times 1 over n. If I had a 1 plus 1 over n, then I was doing a different type of prediction. Anyway, extremely important. So hopefully you get that down. All right, so next thing I do is I just bind the new data with the predictions I get from the previous. I just called it all data because I'm just not very clever. Next thing, I download library ggplot2. Now this is a package that I use quite often in R, and I use it when I teach 6620, so it was already installed on my machine. If you type library ggplot, or you type any package, and it doesn't recognize it, then you have to go back and do an install. Now notice when you do install.packages, the package that you're installing has to be in quotation. However, when you access the library for that package, that is not in quotation. Okay, so anyway, I just access the library because it's already been there. Then I type this mess, and there's a lot there, and I'm going to go back up and demonstrate that. But when you run that, you really get a cool illustration of the confidence bands. So again, the mean was 25 something, I forget. Yeah, something like that, 25.1. So the mean would be right around in here. Can you notice that the band is the narrowest? We get pretty good predictions around the mean. But when we get down here on a tricep measure around 15, 16, something like that, you can see that there's a lot of variation. And somewhat there's a lot of variation up here around 31 or 32. Anyway, the point is, that part is controlled by, let me bring this back up. That part is controlled by this part right here, the numerator, where we're looking at the difference of the x sub h and the mean and squaring it. So the further we are from the mean, the bigger this value gets, hence the bigger the standard deviation, well, the bigger the variance gets, hence the bigger the standard deviation gets. So, yeah, I think that just about takes care of it. Yeah, I can't think of anything else. So, take care.